let's take a look at some of the math behind this. I mean, this is sort of mathy, but let's take a look at the wave functions. We'll come back and take a look at all the quantum states in terms of their quantum numbers. But let's see what solutions actually appear from the Schrodinger equation. So that's probably a good thing for us to start looking at. So let's do one more thing with these quantum numbers. What we can do is set up kind of a diagram. So what we could do for electrons inside hydrogen, inside atoms in general, it turns out, is we can identify, or we can set out a pattern of the quantum states that we're looking at. So what I'm going to do is this. Let me say that I have these energy levels. N is equal to 1, N is equal to 2, 3, maybe I'll do 4. Maybe 4 is maybe enough. So I've got these different energy levels of the quantum states. We found out that the N quantum numbers provide us information about energy. But then we also found out that there are these orbital angular momentums. Now, we said that for different amounts of orbital angular momentum, we have given, well, a name, I guess. It's not much of a name, it's just one letter. If L is equal to 0, we refer to that as an S state. If it's L is equal to 1, we call that a P state. That's a little p. SPD for L is equal to 2. SPDF, G, H. So this is just the vocabulary that we use in describing these states. So if I've got all of these quantum states lined up where L is equal to 0, well, those are all S states. And that would say that something at the lowest energy with no angular momentum is considered to be, it gets labeled as a 1s state. And then state number 2 would be a 2s state. State number 3 would be a 3s. State number 4 would be a 4s, and then that pattern just continues. Now, I haven't spaced the energy states properly. I'm just trying to get a table set up. So we're just saying that as we go up in n value, the energy goes up. 1s, 2s, 3s, 4s states. Now, when we move on to L is equal to 1, then what's going to happen is I'm going to have a series of P states. Now, the P states exist for n is equal to 1 or n is equal to 2. But that's it. You can't have more angular momentum unless the n value is larger. And when we get up to level 3, that's enough energy that we have states in terms of angular momentum that are 3s, 3p, and 3d. And then when we get up to 4, this is 4s, 4p, 4d, and 4f. Again, following the naming pattern that has been set up for for stating how much angular momentum there is in a particular state. So that's kind of interesting. Again, we can see there's more complexity here working through the Schrodinger equation. And the complexity is coming because of all the different angular momentum states that are possible. Let's push this a little farther. As long as we are looking at these quantum numbers, I think we'll hold off a bit on looking at those wave functions. Let's take a look at what kind of predictions this pattern is making for us. So let's do this. Again, let's start with a table. Let's say the orbital angular momentum is 0. 1, 2, 3. That's enough states for us to take a look at and see the pattern. If L is equal to 0, 1, 2, then M sub L, what are the possible values of M sub L that go along with those? And if L is equal to 0, then M sub L can only be 0. If L is equal to 1, M sub L could be -1, 0, or +1. There's 3 possible orientations. Once we get into these p states, there is some angular momentum. And, the way you would think about this is there's angular momentum possibility of kind of mostly spin up predominantly, and predominantly spin down. And then there's one where the spin is kind of in an equatorial plane. And that also is undetermined. But we know that there's not much, and there's 0 in the z direction. So those are what these 3 spin orientations would correspond to. When we get to the d states, that number of orientations grows. So let me get these filled in, and then we'll talk about the pattern that is showing up here. All right. Now, here we only have one possible M sub L state. Here we've got 3. Here we've got 5. Here we've got 7. We can see what's going to happen here is it's just going to go up by odd numbers, right? Since every time we increase L by 1, the M sub L has 2 more possible orientations than it had before. Now, what we're going to do is add to that. So if we say, for a particular set of L and M sub L, let's put in the S and the M sub S. Now, we know that the S is always going to be 1/2. So as we go down through these different possible values of L, the S's aren't changing. Now, the M sub S's for each state could be plus or minus 1/2. Plus or minus 1/2, plus or minus 1/2. So what we're trying to get at here is, you see this quantum state that we've designated as 1s. Is that one state, or is there some multiple number of states that are present in 1s? And so what we can see is, well, if I'm in a 1s state, the possibilities here how many states do we have? And what I can do is I can take one possible orientation from here and 2 possible orientations of spin. So that says that the number of states, 1 times 2, is going to be 2. So there's one possibility here. I guess I should write this the other way. Maybe it'll match up better. Let me do that. We'll say 2 times 1 is equal to 2. When I step down to the next level, this is going to be 2 possible spin orientations, and for each of these possible values of M sub L, there are going to be 3 possible M sub L's. So 2 possibilities times 3 possibilities gives us 6, and if I continue again with that pattern, I'm going to get the numbers 2, 6, 10, and 14. And these tables continue, but this is enough to see what the pattern looks like. So that says anytime I'm in an S or a P or a D or an F set of states, that's going to determine how many states are possible. So in our diagram here, where we're outlining angular momentum and energy, what that says is anywhere there's an S state, there's really two. That's electrons spin up and spin down. So what we can say is in this column, everything in this column is going to have two possible states, spin up, spin down. Anything in this column, so if we move on to the P's, anything here is going to have actually 6 states. Because what we have are m sub L, values of -1, 0, +1. And then we can have spin up, spin down for the electrons in those states. So 2 states in this column, 6 states for each of these, and if we continue the pattern into the D's and the F's, we're going to end up with our 10 states, 5 possible m sub L's, and then spin up, spin down for each of those, and then finally 14 states. Or not finally, but as the pattern continues, 14 states. So that's an interesting pattern and kind of a numerology based on, not a numerology, but based on counting the number of possible states that spin and orbital angular momentum allows for us at each one of these energy levels. And I was thinking, 2 states, 6 states, 10 states, 14. Where have I seen those numbers? 2, 6, 10, 14 states. They look familiar. Oh yeah, it's the periodic table. Because if I look at the periodic table, what I've got are these elements in these first 2 columns that are filling up their S states. And then the 6s, let's see, there's groups of 6 elements over here, the P block, where the states are filling up electrons into P states, and there's 6 total electrons that will fit into those. And then I've got these transition and intertransition regions. Now, traditionally, the way we look at this is the transition elements, these blocks of 10 elements across, those are elements that are filling the D states, 10 states each. And then finally, these intertransition, or rare earths, are 14 across. Now, when you look at periodic tables, they don't quite match up a lot of times. So I'm thinking what I have to do with this one, for example, is in terms of the S states, well, clearly down here, if I put 1 electron into a 1s state, that's going to represent hydrogen, but where is element number 2, helium? And they put it way over there. So, scissor time, right? So what we need to do is we need to cut off the helium block over here, at least in terms of which states are being filled, and bring it back over so it's next to hydrogen. So that's the first change we have to make. Now, of course, helium is over there because chemically it's non-reactive, similar to the elements in that column, but based purely on occupation of quantum states, helium belongs over here in the S column. Then the other thing we have to do here, the block of 6 looks good. The block of 10 are missing 2 elements. So again, it's scissor time. What we need to do is take a lanthanum and actinium, cut those out and move them into those slots. Now, when we do that, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, exactly. There were 15 elements down here. These are inner transitions. They belong up here as transitions. And then once we do that, we're done. Now, since this periodic table was put together, we now have identified, researchers in different labs around the planet have discovered and named additional elements all the way out to element number 118, I believe. So that row right there is filled, but you know, with a few changes, everything's going to work fine with our periodic table. All right, so imagine the excitement back in the late 1920s, early 1930s. Once physicists had mapped out all the possible energy states, what they realized was the Schrodinger equation predicts the periodic table. We can predict what the pattern of electrons will be. We can kind of predict the existence of a series of elements. The elements are determined by how many protons are in the nucleus. And then for a neutral atom, that means that you're going to be filling the atoms with electrons in these different possible states. And so as you move from one element to the next, that's one additional proton. That means that a neutral atom could accommodate one additional electron. So again, moving through the periodic table, we can fill these S states, move up to the next S states, fill the P states, move up to the next level, fill the S, fill the P, fill the D, move to the next level. Now, it's not quite as simple as filling them in the order that we've set up here. It turns out that the energies that we get for these electrons only work for hydrogen. Once we put more than one electron into these atoms, the energy levels do not continue to match up. And by that what I mean is, once we start putting electrons into the 1s and the 2s and the 2p states, it turns out that no longer are the 3s, the 3p, and the 3d at the same energy. Okay, so there's complications, and we'll take a look at some of that a bit later, but hey, that's pretty remarkable. You start out with this partial differential equation based on energy and momentum and angular momentum operators, and you derive the periodic table. That there should exist a series of elements with these patterns of electrons to them, and once you know the pattern of electron, you know what the chemical properties will be for that particular element. So, pretty powerful that the Schrodinger equation was able to make all of these predictions. All right, let's move on from this. What we keep promising is that we're going to actually take a look at some of these wave functions, so let's do this. And we'll leave some of this up here for now as much as we can. What we want to do is go back to hydrogen, exclusively hydrogen. Turns out that hydrogen, a neutral hydrogen atom, has just one electron. And the Schrodinger equation that we have solved so far really just applies to atoms with one electron. Now, it does turn out, looking ahead, everything we've done in terms of angular momentum still works. The energies get disrupted. We talked about that a bit, that the energy levels, you know, the 3s and the 3p and the 3d aren't going to maintain the same energies. Those are all going to change. So the energy levels are going to get disrupted. But angular momentum is unaffected. So if I look at complicated atoms, you know, if I'm looking at uranium with 92 electrons, the energy level calculations are going to be a mess to try and figure out. But and even that's a bit of an exaggeration. There's still a pattern that we can work from. But the angular momentum calculations remain exact. So we can still designate specific amounts of angular momentum for each of the electrons in something as complicated as uranium. All right, hydrogen, let's get back to that. So here is our hydrogen atom. Now it turns out that I've been drawing the hydrogen atom this way. I've been saying, all right, there's a proton, it's really got a lot of mass, it's sitting there at the center, and then the electron is going to have a wave function. And that wave function is going to be given in spherical coordinates. So I'm writing the wave function, and what I'll also do here is I'll put a little 1s here. I'll say this specifically is the 1s state for an electron in hydrogen. So the 2s, all these different quantum states that we've talked about are going to mathematically have different wave functions to them. So we're going to start off with the simplest one. And it turns out this one's not too bad. When we solve the differential equation, the Schrodinger equation, that this all starts from, it turns out that the 1s quantum state of hydrogen has a pretty simple formula to it. There's a normalization constant out front. We've seen those before from chapter 38. And now what it's saying is it just drops off exponentially. So the wave function starts out, if we plot this function, what does it look like? Let's take a look and see. So here is the wave function as a function of r. Now, what I am going to do here is, let me cross out some stuff. I'm going to cross out the theta and the phi dependence, because in general, the wave functions could have theta and phi dependence, but it turns out the 1s state does not. In fact, it turns out that none of the s states have any theta or phi dependence. That s states are spherically symmetric. So this kind of spherical shape that I drew works pretty well as long as we're limiting ourselves to the 1s, 2s, 3s, 4s, etc. As long as it's an s state, there's no angular momentum, and at the quantum level of electrons inside atoms, no angular momentum means spherically symmetric. It's the shape that tells us what the angular momentum is. Kind of interesting. So, taking a look at this function that I've got here, it says that the wave function, the 1s wave function, starts off at some value of a, and then it drops off exponentially with r. Now, little a is some kind of a scaling factor, right? So little a is giving us an idea of how spread out the wave function is. And you know what that's really telling us is how big are atoms. So the scaling factor of a right there is eventually, we're going to go back and see what that value is. And that's a prediction of how big an atom would be. So that's going to be kind of interesting. Now, if I just take a look at this wave function itself, what it's saying is that the wave function has its highest value right at the center. So if I were, let me pick a few points on here. Let's say here's point A, and here's point B, and here's point C. You pick some regions in space. At which of these locations does the wave function have its largest value? And as far as the 1s state is concerned, A has the largest value, B it's dropping off exponentially, and then C it's dropping off even more. So A would have a higher value, B and C would have the least. If I keep moving away from the atom, now remember these kind of spherical boundaries that we've drawn, they're not really boundaries. There's not a definite cutoff for where the electron is located. What this wave function is telling us, is that as you move farther and farther from the nucleus, the electron probability drops off more and more. Okay? So it's going to get less and less likely to find the electron as you move farther away. So you just kind of have to use some kind of an estimate and say at some point we're going to say the atom is this big, even though there's always, whatever boundary you draw, there's always going to be probability outside that, some finite amount. Okay, it's one of those functions that you lose sleep over, right? When does it ever go to 0? It just asymptotically approaches 0. All right, so if this is the wave function, and the wave function is dropping off, maybe the next question we would ask then is, well, how do I represent probability? So what we would like to do is come up with a probability distribution What's the probability distribution for the 1s quantum state of an electron in hydrogen? And we know how to get that. We know that a probability distribution is going to be given by taking our wave function and modulo squaring it, or just squaring it. In this case, since the wave function we have here is completely real, there's no imaginary stuff, there's no i's, factors going on here, then modulo square is the same thing as squaring. But if we square that wave function, what that's going to give us is a squared e to the minus 2r over a. So we talked about the value of the wave function itself. Now, all of you know that exponential functions show up in physics all the time. So in physics and other fields of science, chemistry, biology, we run into these exponential functions all the time. And something that I feel like you should be aware of is that if I have a scaling factor written in an exponential this cleanly, so if I just got the variable divided by scaling factor with a minus sign and there's an e there, these show up all the time. What that a is telling me is the distance at which the function has dropped off to 1 over e. If I get out to a distance r that equals a, oh, sorry, wrong function. If I get out to a value of r that equals a, what I'm going to have inside here is a factor of e to the minus 1. And it turns out that e to the minus 1 is about 37%. Now, what I'm always telling students is, you know, if it was a half-life, we're often working in terms of how much distance until the function drops to half of its value. Well, instead of dropping to 50%, the way exponentials work is one scaling factor of distance drops us down to 37%. And then a second scaling factor, you know, if I go out to 2a, for example, so 2a would drop us down to 37% of 37%. And 3a, the wave function would be down to 37% of 37% of 37%. So these drop off to something like 14%. If you get all the way out to 3a, the wave function itself is going to be like 5%. So anyway, just so you're kind of familiar with how scaling functions work, because it's just a fact that we work in exponentials a lot. So this is now my probability distribution, and now conceptually, one way to think about this is, hey, if that's, I'm going to call this probability per volume, because that's what it is. Okay? So that says if I picked a little volume right here, and I picked a little volume right here, and a little bit of volume right there, and I match all the volumes. Let's say, just for thinking about this, that the volumes we're looking at are 1 cubic picometer. Now, picometers are handy when you get looking at distances inside atoms, and that's because your typical atom is maybe 100, 200 picometers across. So most of the probability in an atom is within a few hundred picometers. Now, that says that if I pick 1 cubic picometer, that represents a little tiny region. And if I pick a little tiny region, then this wave function isn't changing very rapidly over that region, and I can just look at the values of these wave functions and the probabilities and assign those to these different blocks. So again, we can come back and ask the question, well, where is the probability the greatest? 1 cubic picometer block right at the nucleus, 1 out here at point B, 1 out at C, 1 out at D. And what the wave function squared is telling us is that, again, just like the wave function itself, the probability distribution is going to have the highest value right at the center, and then as I move away from the center, the probability is going to drop off, going to drop off even more, drop off even more. Now, that's in the situation where we're considering these little boxes, one at a time, of similar volume. Now, there's a couple of issues that come up here, and the first thing is, wait a minute, can two particles occupy the same space? Absolutely. So what we find out in quantum mechanics is these electron wave functions, they all overlap with each other. So that says that if I look at any atom that has more than one electron, those electron wave functions are overlapping with each other. So definitely the probability distributions can overlap. And that says, yeah, actually the most likely location for an electron is right where it overlaps with the wave function from the proton. Okay, so I got a proton wave function, electron wave function. Electron wave function is much more spread out, but they both peak at the same location at the center. All right, so that's what this probability volume is telling me. Now, there's kind of a second way that we think, ooh, I got to draw the graphs. Let me draw the graph. So now let's draw the wave function squared graph. That's also going to start off with the largest value at r equals 0. Now, this time, the peak value is going to be like a squared, where a is a normalization constant. And what we're going to do is we're going to have something that's dropping off even more rapidly. Since it's an exponential squared from what it was before, the drop-off distance is going to be shortened by a factor of 2. I'm just going to draw this. Okay, so that is probability, density, dropping off with distance. Now that's the wave function squared. So what we have to do here is, let's see, there's the wave function. You want to understand how to draw out graphs on that. There is the wave function squared, which is our probability. There's one more function that we make use of very commonly, and that is a function that is this. It's 4 pi r squared times the wave function. You're thinking, 4 pi r squared, where have I seen that? Well, what 4 pi r squared times the wave function squared looks like is this. And you're thinking, oh yeah, that looks much more like what I've seen in my chemistry books. If I look at the probability distribution for the 1s state, the probability at the center goes to 0, right? Well, let's stop and think about what this wave function is actually telling us. This is not a probability per volume. What it is this is a probability per spherical shell. So let's go back. Let's say that we wanted to integrate all the probabilities everywhere. What would we have to do? And to integrate all the probabilities everywhere, we would have to go back to our spherical coordinate diagram. We would have to identify a volume element. Now, you guys remember from your calculus classes, I guess it's, what, Calc 3, working in multidimensional calculus. In spherical coordinates, the volume element is given by a little cube, and that little cube has a distance of dr, that's in the direction away from or towards the nucleus. And then it has another side that has dimension r sine, r d theta. And that's in this direction. That's measuring from the top towards the equator. Now, in the earlier part of today's lecture, we went through the coordinate system that is convention in physics. And I think math has moved on to a more sensible set of coordinates, but physics has maintained, for better or worse, we still think of theta as coming from the axis downwards, and then phi is really keeping track of where we are in the xy plane. So if you think of kind of rotating through the xy plane, that's what phi is keeping track of. And you're saying, wait, but doesn't that contradict with polar coordinates? And you'd be right. Anyway, for spherical coordinates, that's what we're using. These little volume elements, these three-dimensional volume elements, have a distance of dr here. They have a distance of r d theta here. Let me draw that line in so we can see it. And then in this kind of latitude direction, what they have is a distance that's r sine theta d phi. Now you can go back to your calculus book to see details of this, or you can see it in the, if you've forgotten how this works. We've got a diagram right. If you remember how this works, then, and from this diagram you can see it. But, you know, go back and either take a look at our textbook, which would work. If you need to, maybe go back and review how this all works. Anyway, what's happening here then is if I were to integrate all the probability, I would have to carry out this three-dimensional integration. But what we can do as a first step, what we can do is rather than starting off with these volume elements, or these little boxes, and then, yeah, these volume elements, I guess, and integrating them over all possible values of r, theta, and phi, what we can do is recognize that for the S states, everything is spherically symmetric. So what I can do is think in terms of not just individual boxes, but entire spherical shells. So let's say for point B, instead of using a block of 1 cubic picometer, what if we take an entire spherical shell? And then once we get out to point C, we'll take the shell out there. Now, the way we're going to make use of this spherical symmetry and use shells probability instead of individual volume probability, we're going to do shell probability. We can put a factor of 4 pi r squared, because 4 pi r squared is the surface area of those spherical shells. Now what happens then is, if I'm thinking in terms of this function, instead of a probability per volume, I'm thinking in probability per shell, well, that changes things, right? If we were playing roulette, right? You walk up to the roulette table. If it's set up as all these little boxes, which box are you going to place your bet on? And I go, I'm going to bet on that box right in the middle, because that's the highest probability. But what if roulette's set up so that instead of picking individual boxes, you pick values of r, which include the entire spherical shell? Then, well, all bets are off. But what I want to do is, well, if I'm betting on shells, then I don't want the one in the middle. I want one that's farther out. I want one that's out here, where that function peaks. So there's going to be two offsetting effects here. What happens is the wave function itself and the wave function squared are dropping off exponentially with distance. But as I move from the center of the atom outwards through these spherical shells, the shells are getting bigger. Now the shells are getting bigger according to 4 pi r squared, right? And that's just a polynomial, second order polynomial. That's not such an enormous increase. The exponential drop-off is going to eventually take over. But at least initially, there's going to be this effect where the probability per shell goes to 0 at the center. Now, that sounds kind of like a paradox because we said, how can the probability per volume be equal to its highest value right at the center, but the probability per shell is 0 at the center, and that's because the shell right at the center has no volume. So it's really kind of unfair. This function, this 4 pi r squared function, is a little misleading because it might lead us to think that there's no probability at the center when in fact, volume for volume, that's where the probability is the very highest. Anyway, be familiar, know the difference between these three functions, know how to draw a rough diagram of these functions. Make sure that you can draw those out and provide information about each of those. Okay, questions on any of that? We've got a little bit more time here, so let's see how far we can get with this before we end for the day. We've got this nice spherical coordinate system set up here. I was thinking maybe just for practice, let's see if we could derive a formula for the volume of a sphere. So I got this stuff in the middle of the board. I've got the picture over here, but I'm going to do some math at this side. That'll make sense, right? So let's try solving for the volume of a sphere. Let's derive it using integral calculus. So if I'm going to solve for a volume of a sphere, what I want to do is take each of these little volume elements and add them all together. So each of these individual volume elements are going to have a certain amount of volume to them. There's a numerical value you can calculate, and they're going to have units. So there's going to be some units associated with each of these. Now, to get the total volume, what I can do is add all the little pieces together. Now, to do that, what I'm going to need to do is, I need to do integrations in r, theta, and phi. For r, what I've got here is r squared dr. And that comes because I've got a factor of r in this direction, I've got a factor of r here, and I have a factor of dr in the r direction itself. Now, for a sphere, what I could do is integrate from 0 out to the radius of the sphere. So that's my plan right now, is to carry out that integration. Now, the next integral that we want to look at, let's do the thetas. So if I look at all the theta dependents, what I have here is sine theta, d theta. What's the range of values that I would want to use for theta? And for theta, what I have to do is, theta is equal to 0 at the top. And then theta, in order to pick up every one of these rings that we've got, or each one of these layers, I have to go from theta equals 0 to theta equals pi. There's no need to come all the way back, because as I look at each layer, each value of theta is going to correspond to a different level in my sphere. So if I think of the sphere as broken up into a series of levels like this, going from 0 to pi is going to work for that. And then finally, what's my phi dependence? And the phi dependence here is just one factor of d phi. That's it. That's all I have. So for d phi, I'm going to go from 0 to 2 pi. For the phi, we need to go all the way around the entire circle at each level. So going back to what we've done here, so the d phi goes all the way around in a circle of 2 pi, and then to pick up each one of those layers, I'm going to go from theta from 0 to pi, and then finally to take all the possible values of r from 0 out to the radius of the sphere. We'll use this. So this is our practice using spherical coordinates to calculate a volume in this case. All right, what factors am I going to come up with? And if I carry out this integration, what I'm going to get is 1/3 r to the 3rd power. Now this integrates to be cosine theta evaluated between 0 and pi, and that becomes 1 minus a minus 1. It actually gives us a factor of 2. You can check that. So that's going to give us a factor of 2. And then finally the d phi is going to leave us with a factor of 2 pi. So what this says is that once we've correctly identified the volume element to work in for spherical coordinates, we can then derive a formula for the radius of a sphere, and it looks like it works out to be 4 pi over 3 r to the 3rd. So that's a good thing to know, right? So that's how we carry out three-dimensional integrations in spherical coordinates. Now, for our purposes then, what we want to be doing, take one more look at that, I guess. What we want to do is, maybe we can use what's already here. What we'll do is we'll get rid of that volume calculation, and what we'll call it instead is calculating probability. Okay, so to calculate the probability, we would integrate this, but what we have to slip in here now is the wave function. Sorry, hydrogen, I'm going to borrow part of your space. There you go. So that's what the integrations in general are going to look like. Now, for better or worse, the wave functions start out pretty simple. This 1s wave function is not so difficult, but they get more complicated, and they get more complicated pretty fast. So we're going to spend a lot of time looking at this 1s state mathematically, and then we may look at some examples with some other states, but we'll see. We'll see how much time we actually have. In any case, if I'm working with a 1s state, or even a 2s or 3s, anything that's an s state, remember, is not going to have any theta and phi dependence. So if I don't have any theta or phi dependence, what happens to my integration? Well, for any s state, this probability then, one more change, sorry. We have to integrate the r's out to infinity. It's a good thing we caught that before we wrapped up for the day. So that's definitely an integration from 0 to infinity. Now you're thinking, but wait a minute, isn't that going to give us an infinitely large result? You go, no, because the wave function is dropping off exponentially. So you guys, plenty of experience integrating out to infinity and beyond. So anyway, that's the integration that we want. Now, what we can do then, if it's an s state, right? An s state meaning that I don't have to worry about theta, I don't have to worry about phi, then what I can do is I can up front integrate this out to 2, and up front integrate this out to 2 pi. That becomes 4 pi. And so the integrals then look like this. They look like 4 pi r squared wave function, which is now only a function of r, dr. And that's why, for the s states, this becomes an important function for us. Because this is kind of like getting all of the preliminary integration taken care of. What we've done by using that function is taking an integration that was in 3 dimensions and reducing it down to 1. So anyway, that's where we're going to pick up in the next lecture, which I guess is officially Wednesday. But that's what we're going to be looking at. So this becomes, let me just write this in. What we've done is show that this is the probability per shell. And to calculate a probability now, what we can do is, if it's 0 to infinity, then it's going to integrate out to be 1. And that's going to allow us to carry out the normalization. Okay, so that's where normalization will come from. Okay, let's stop. That's a good time to stop. Again, we'll just pick up right here for the next class meeting.